Okay, we're going to shift our discussion now to molecular compounds instead of ionic compounds. Remember when we talked about ionic compounds, we were talking about metals and nonmetals that form compounds together, or compounds that form that have polyatomic ions in them. Okay, when we're talking about molecular compounds, we're talking about nonmetals that are forming compounds. And the way that they form compounds is a little bit different. There's going to be a different naming system for that because they are forming compounds differently. Um, they're also forming compounds using that different type of bond, that covalent bond instead. So we're going to look at a few parts of molecular compounds now. So when we have our molecular compounds, we're going to have two or more nonmetals. You can have many different nonmetals that are bonded together, and they're going to share electrons. That's different than ionic bonds. Remember, ionic bonds, we're transferring electrons, but with molecular compounds, we're going to be sharing electrons. And that type of bond is called a covalent bond. And by sharing electrons, each nonmetal is going to receive enough electrons to become stable. Okay, so remember, everything's still, well, most everything except for like an element like hydrogen is looking to have 8 electrons around it. Okay. So even with this method, they're just going to share electrons so that they have 8 electrons that are associated with them, and then they become more stable. These are the prefixes that we're going to use to name our molecular compounds, because when we're naming molecular compounds, they can combine in a lot of different combinations. They're not limited the way that ionic compounds are. Remember that ionic compounds have to combine in ways that will cancel out charges overall. But with molecular compounds, because they're not transferring electrons, they're not going to be combining based on charge cancellation. So that means that you can have two elements combined in a whole bunch of different ways because they're just sharing electrons with each other. So we're going to use prefixes to tell us exactly how many atoms of each element are present in that compound. But you have to remember that these prefixes are only used for molecular compounds. You never use prefixes when you're naming ionic compounds. All right. And that's a tricky thing to sort out. And especially if you're taking like a multiple choice type of test, you will see ionic compounds given that have prefixes as answer choices, just to make sure that you understand the difference between those two. All right. So when we're naming molecular compounds, we're going to use a prefix that represents the number of atoms that are present. Then we'll write down the name of the first element. Then we'll use another prefix to tell us how many atoms of the second element there are. And then we're going to do the same thing we did with the ending of the ionic compounds, where we will take the first syllable of that last element's name, and then we'll add an IDE ending to that. Okay. The only time you do not need to use a prefix is if there's only one atom of the first element that's present. In that case, you can leave the mono prefix out. But other than that, every element needs a prefix when you're naming an ionic compound. Okay. Yep, the slide pretty much says the same thing. So let's look at these two examples that they've given us here. We have CO2 and CO. So for CO2, there's one carbon and two oxygens. And so the name for this is going to be carbon dioxide. And the name tells us exactly how many atoms of each thing are present. We know that there's one carbon because there's no prefix in front. And we know that there are two oxygens. For CO, we know that there's one carbon and there's one oxygen because it's monoxide. You're going to notice here that when there was one oxygen, if you wrote down the prefix and the nonmetal side by side, it would have been monooxide. Whenever you have two O's next to each other from the prefix and the nonmetal, that first O gets dropped off. Okay. The same thing will happen if you have something like 5 oxygens, like penta, and then an oxide next to it. that first vowel, that A, is going to get dropped off. And this would just be pentoxide. Okay, so when you have one oxygen, it's going to be monoxide. When you have 5 oxygens, it's going to be pentoxide. So here are just some examples. If you want to look at how these are written out, see when you have 2 nitrogens and 1 oxygen in your compound, N2O, that's going to be dinitrogen, and it should be monoxide there. So bad example there because they forgot the prefix. Here, sulfur trioxide. So we're going to look at some examples and we're going to name using the prefixes. So we'll do these on the board. So our first example they give us is NCl3. And again, we're just going to figure out how many of each atom are present. There's 1 of these. There's 3 of these. And so we name it. Our first element is nitrogen. There's 1 of them. So we'll leave out the mono prefix and we'll just write nitrogen. And then for our second element, we have 3 of them. So we'll start with the prefix tri, and we see that it's chlorine. So we'll write the first syllable of chlorine, and then we'll add the IDE ending. All right, our second example that they give us is B2O3. So we have 2 borons. So for our prefix 2, we'll write di, and then we'll write our boron. And then we have 3 oxygens. So we're going to write trioxide. Okay. We can also look at how we do the reverse process of this. Okay, so let's say that we're given, share the screen again for a second. Let's say that we're given a name of a molecular compound, and we want to know what the formula of that is. We're just going to track backwards. Okay, we're going to use the symbols to tell us which element we're looking at, and we're going to use the subscripts to tell us, or we're going to use the prefixes rather to tell us what the subscripts will be. Okay, so diphosphorus pentoxide. This is telling us that we've got 2 phosphorus and we have 5 oxygens. All right. So when we write that out, look at these examples. Okay, so our element is phosphorus. There's 2 of them. Our second element is oxygen, and there's going to be 5 of them. Okay, our next learning check asks us to write the correct name for each compound that's present. And they're giving us SiCl4. We already did P2O5, so we're not going to do that one again. And then Cl2O7. So here we've got 1 silicon, so we'll just write silicon. And then we've got 4 chlorines, so we're going to write tetra for 4, and then chloride. Here we've got 2 chlorines, so we'll start by writing dichlorine. And then we have 7 oxygens. So instead of writing heptaoxide, we're going to leave the A out. We're going to leave the first vowel out and write heptoxide. Okay. All right. The next slide that's up in your notes talks about how to differentiate between ionic and covalent compounds. And so we're going to make a list on the board to help out with some of this. Okay, so ionic compounds versus molecular compounds. Some of the things that you want to look out for, some of the properties of both. Um, all right, then the first one, compounds. So with your ionic compounds, your first element will either be a metal or it's going to be part of a polyatomic ion. And specifically, the only polyatomic ion that your textbook talks about that's positively charged, that could actually be the first ion in a compound, is going to be the positively charged polyatomic ion ammonium, which is NH4 plus. So if you're looking at a compound and the first element is a metal or the ammonium ion, then you know it's an ionic compound. Your ionic compounds are going to form from ionic bonds, which means electrons are transferred. And your ionic compounds never use prefixes in their names. All right, for your molecular compounds, first of all, these you have to remember that they're also called covalent compounds. And those two phrases are used like interchangeably. You'll see either one. Sometimes people switch back and forth between them because they mean the same thing. And in your molecular compounds, you're going to have only nonmetals. So use your periodic table to help you figure out whether the compound that you're looking at is ionic or molecular. You also have to use your knowledge of your polyatomic ions for this, okay? Because you can't just look at nitrogen. If your compound is NH4Cl, for example, you can't just look at the nitrogen and say, oh, that's a nonmetal, that's a nonmetal, and that's a nonmetal. So this is a molecular compound. You have to recognize the NH4 part and say, that's a polyatomic ion. And if I have a polyatomic ion, then this compound is an ionic compound. All right. So you do have to be able to differentiate between those things. But if you have no polyatomic ions and everything else in your compound is just nonmetals, then it's going to be a molecular compound. And when you have molecular compounds, they're going to form from covalent bonds. Which means that the electrons are going to be shared. And for your molecular compounds, you must use prefixes in the names. Okay? Those are going to be the differences between those two. We could look at the flow chart real quick. The overall naming flow chart. If you could sketch something like this out for yourself, it's very helpful when you're trying to name your compounds. That first, like the first split in your flow chart is going to be whether your compound is ionic or molecular. And you're going to look at your first element or your first, the first part of your compound to figure this out. If the first component in your compound is either a metal or the ammonium ion, then you know that your compound is going to be ionic. If your first element is a nonmetal, and it's not part of the ammonium ion, then your compound's going to be molecular. And then within your ionic compound, you're going to have this first cation, remember, because the first thing is going to be your positively charged thing. The second thing is going to be your negatively charged thing. Within that first compound, you're either going to have two choices there. You're going to have a metal that only has one possible charge, or you're going to have a metal that has two possible charges. When you have a metal that only has one possible charge, you're just going to write the name of the metal, and then you're going to follow it by either the first syllable of your nonmetal with the IDE ending, or if it's a polyatomic ion, you'll follow it with the name of the polyatomic ion with no changes. Okay. If you have a metal that has more than one charge that it can form, you're going to write the name of that metal and you're going to follow it with parentheses that have the Roman numeral representing the charge of the metal inside of them. And then you'll follow that with the same possible endings here. Either if it's an element that ends your compound, you're going to write the first syllable of the element name and then the IDE ending, or you'll write the name of the polyatomic ion that it's attached to. With your molecular compounds, your first nonmetal, you'll use a prefix, unless there's only one of them. You'll use a prefix to match the subscript, and you'll write down the prefix and then the name of the nonmetal. And then for your second, you'll write the prefix that represents how many atoms of that element there are, and then follow it with the first syllable of the non-metal name and end it with that IDE ending. Okay. You could use that flowchart to help you out with your naming while you're practicing it. So we're going to do a few more practices with naming stuff before we move on. So we'll work on the board a little bit. And for any of these, like we've said before, should pause and try these on your own. But for each of these examples, as you go, you're going to decide before you start naming them, is it ionic or molecular? And then once you decide whether it's ionic or molecular, you're going to know whether to use prefixes or not. Once you decide something is ionic, then you're going to have to do your second decision making and decide whether it's a metal that only has one charge or whether it has more than one charge. Okay. So here we have SO3. Sulfur is a nonmetal. Oxygen is a nonmetal. So this is going to be a molecular compound. So if it's a molecular compound, we're going to use prefixes to name it. So we have one sulfur, so we'll just write down sulfur. And then we have 3 oxygens, so we're going to write down trioxide. For our second compound, barium is a metal, chlorine is a nonmetal, so we know that this is going to be ionic. When we look at the barium metal, we see that it's in the second column. Barium only has one charge. So we're going to just put the name of the barium. We don't need parentheses for this because barium only has one charge. And then we're going to write the first prefix of chlorine and then change the ending to IDE. All right, for our next one, we're going to recognize that we have a polyatomic ion here, and it's followed by another polyatomic ion. So that's going to be an ionic compound. And to name ionic compounds with polyatomic ions in them, we just need to write the names of the polyatomic ions down. No changes, no parentheses. This is going to be called ammonium phosphite. The name of the ammonium ion, the name of the phosphite ion. Here we have copper and we have the carbonate ion. So we have a metal and a polyatomic ion. So this is going to be an ionic compound. copper has more than one charge. So we need parentheses to tell us the charge. Okay. Let's erase that last one for a minute so we can figure out the charge, because once you decide you need parentheses in your name, you have to look back at your compound and you have to use the compound formula to help you figure out the name. We have one carbonate ion. I guess I should have left that there because we could say that the carbonate ion we know has a -2 charge. And we have two coppers. And we know that because it's an ionic compound, the copper charges have to add up to cancel out the carbonate charge. So when we look at it this way, we could see that each copper is going to have a +1 charge on it. Okay, because now we have +1, +1, that's +2. This is a -2. So now they're equal and they neutralize. So now when we write out the name for the compound, we're going to write the name of the metal. Then in parentheses, we're going to write the charge on the copper. So we're going to write a 1 in parentheses. And then we're going to write the name of the polyatomic ion. Okay. And then that last example we had was N2O4. Nitrogen is a nonmetal. Oxygen is a nonmetal. This is going to be a molecular compound. And so we are going to just name it using our prefixes. We have 2 nitrogens. So our first part of our name is going to be dinitrogen. And we have 4 oxygens. So we see that the prefix for 4 is tetra, and we're going to add oxide after that. So we're going to leave out the first vowel, and we're just going to write tetroxide. All right, so instead of tetraoxide, tetroxide. All right, let's look at our next section. We're going to start to look at Lewis structures now. Okay, and Lewis structures are going to be the way that we can represent the molecules that form when covalent bonds are happening. We can write these Lewis structures down for neutral molecules, and we can also write them down for polyatomic ions, because remember, polyatomic ions are just a bunch of nonmetals that have covalently bonded together and ended up with a charge overall. But they're still created from these covalent bonds. So these are just some examples of what some of these Lewis structures will look like, but we'll take a look at how we actually work with them. Starting out with your simplest molecule, H2. When you have hydrogen, when you think about your hydrogen atom, each hydrogen atom, we have a picture of it here, each hydrogen atom has 1 electron in it, right? When the atoms are kind of far apart, they're not going to be attracted to each other. But as they move closer together, the electron from one hydrogen is going to get pulled into like the kind of like the proton, the positive charge for the other hydrogen, but also like every atom has, space to fill their outer shell, right? We talked about the valence shell, and hydrogen has, it has a 1s valence shell, and your s sublevels, they want 2 electrons in them. So hydrogen, when it's by itself, it only has 1 electron in that outer shell. And it wants 2 electrons in that outer shell to make it stable. And so when these hydrogens get closer together, they kind of recognize that each one has an electron that the other one needs. And so when they get close enough, they can sit here, and now they can both share electrons so that each of them have that filled 1s sublevel. So now they both get to have that full valence shell, the full outer shell. And that's how your covalent bonding is going to work. You're going to end up with these molecules that are sharing their valence electrons, and those shared electrons form the covalent bond. Okay. When you're looking at Lewis structures, when you're looking at the molecules, you're going to see bonds form. Okay. And the bonds are going to represent those shared electrons. You're also going to see dots that appear on top of the different elements. Those dots are going to represent electrons that belong just to the atom that they're attached to. So in this particular molecule, which is ammonia, NH3, the lines represent the shared electrons between the hydrogen and the nitrogen. So we call those bonding electrons or bonding pairs or bonding groups. And then these two dots represent a lone pair of electrons that belongs only to the nitrogen. Okay, these are going to be non-bonding pairs. And when we write out Lewis structures, we're gonna basically be looking at our atoms, and we're gonna see how they start out with their individual valence electrons, and when they come together, how they finalize their form to have the 8 valence electrons that they need to form a stable molecule. So here in our example, each fluorine has 7 valence electrons, which we know because remember that for our elements from 1A to 7A on our periodic table, we can use that group number to tell us how many valence electrons each atom has. So fluorine is in group 7A. So fluorine has 7 valence electrons and it wants 8. So when the two fluorine molecules approach each other, they kind of reach looking at that single electron that they have, and they're like, all right, let's each share one. And that shared overlap, that becomes the covalent bond. And that's how you get your fluorine molecule, which would be F2. There are there's 7 elements on your periodic table that you really have to be aware of that form these diatomic molecules. These particular elements, they do not exist as single atoms naturally. Okay, because by themselves, they are extremely unstable. So if you have like hydrogen gas or oxygen gas that you're, working with, that you're looking at, that gas that you're looking at is going to be, it's going to be made of these molecules of these particular elements. You're never going to have them as just single atoms. Because if you have 2 nitrogen atoms next to each other, for example, they're just going to pair up and they're going to form a nitrogen molecule because it makes them more stable. For the same reason that we saw fluorine do it here, right? Because like fluorine by itself is missing that last electron that it needs. But once it pairs up, now it's stable. So if you have fluorine gas, it's just going to exist as a whole bunch of F2 molecules that are floating around in that space. If you want to picture it that way. We can also use the groups on our periodic table to get a good idea of how many bonds each type of element wants to form. The group number corresponds to the number of bonds that most nonmetals would like to form. Okay, this is their most stable forms. So like things that are in, that works the same way that charges do, right? When we had stuff that was in group 1, it had a positive 1 charge. Well, hydrogen's in group 1 and it just wants to form 1 bond. In group 3A, you have boron. It just wants to form 3 bonds. Carbon is in group 4, wants to form 4 bonds. When you get over to group 5, instead of the numbers representing the number of bonds that are forming for 5, 6, and 7, this is going to work the same way that our charges did. So instead of saying that group 5A wants to form 5 bonds, we're going to think, oh, group A has 5 valence electrons, so it's going to form 3 bonds to get up to 8. Okay, so You'll notice that 5 plus 3 is 8. 6 plus 2 is 8. So when you have nitrogen and phosphorus, these things typically form 3 bonds to get to their stable structure. Oxygen and sulfur will typically form 2 bonds. And then your halogens will typically form 1 bond in group 7 to get to their stable structure. Okay. And we'll look at how that works out when we go through the process of how to draw the Lewis structures. One way that you can draw Lewis structures when the Lewis structures are a little bit simpler is that you can write out the Lewis symbols for each element, and then you can just sort of see where they're going to connect to each other, and this connection will form the covalent bond. So if carbon and hydrogen are going to form a compound together, each hydrogen will surround the carbon, and they'll share the electrons that meet there. When you're looking at Lewis structures, there's just a little terminology that you should be familiar with. In the center of each Lewis structure, there's going to be an atom that everything else is connected to. Okay. And we're going to call those atoms the central atoms. So in our examples here, the carbon, the nitrogen, and the oxygen are our central atoms. Okay. Then there's going to be atoms that are only connected to one other thing, and they appear at the ends of our molecules. And we're going to call those types of atoms terminal atoms. So they're only connected to one other thing. Okay. Those are terminal atoms. In our periodic table, no. In our Lewis structures, we're also going to see double bonds and triple bonds sometimes. Okay. There's a reason when you see double bonds and triple bonds. They don't just show up randomly. They don't just show up because we want to throw a double bond somewhere. When you have a double bond forming, that's happening because there are not enough electrons for everything in your structure to receive an octet with a single bond. The same thing for a triple bond. This is going to occur when there are not enough electrons to complete octets. And a double bond means that you have an atom that shares, you have an atom on one side and an atom on the other side, and they're sharing 2 pairs of electrons instead of 1 pair of electrons. So they're making 2 bonds instead of 1 bond. And for a triple bond, you have 2 atoms, 1 on each side, and they're sharing 3 pairs of electrons instead of 1 pair of electrons. So these are what double bonds would look like. This is what a triple bond would look like. And remember, each line represents 2 electrons that are part of that bond. The element's tendency to want 8 electrons it has a name. It is called the octet rule because most elements want 8 electrons. There are going to be exceptions to the octet rule. We're going to see that with hydrogen for sure, because hydrogen is so small that it only needs 2 electrons to get to its most stable structure. Another element that is very small that breaks the octet rule is boron. Boron only needs 6 electrons around it, and then it's perfectly stable. On the other side of that, there are also going to be some nonmetals that will increase the number of electrons that they can hold. Okay. So nonmetals, these are just some examples of them, like phosphorus, sulfur, chlorine, bromine, and iodine. They can actually expand their octets. And instead of just holding 8 electrons, they can hold 10 or even 12. We're not going to focus very much on these expanded octets. We're going to stick mostly to molecules that are going to follow the octet rule. So let's look at a step-by-step way of how you can write down Lewis structures for your molecules. If you follow this method, then when you're writing out a Lewis structure, you'll always end up with the right structure. Okay. So the first thing that you're going to do is you're going to look at all of the elements that make up your compound. and you're going to count up the total number of valence electrons that are available for your structure. Okay. So, like when all of your atoms are coming together to make these compounds, they're all going to be coming in, bringing their own valence electrons. And so, we're going to count up how many valence electrons everything has altogether. Okay. Then we're going to connect the atoms to each other in the most logical way. We're going to decide what goes in the middle. You can decide it one of two ways. You can put the least electronegative atom in the middle, and we'll discuss electronegativity in a few slides, so that'll make more sense. But if you have a compound like PCl3 and you have one phosphorus and you have three chlorines, you can be comfortable putting the phosphorus in the middle because there's only one phosphorus. Okay, so like if you only have one of a particular element, that's the thing that you can put into the middle. All right. And then that will usually correlate with the least electronegative. So those two things usually go together. So you can kind of use either method to figure out what goes in the middle. Your hydrogen atoms should always be in those terminal positions. So they should always be like around the ends of your molecule. And then hopefully, if you've done this first step correctly, then your more electronegative atoms will always end up in the terminal positions out on the ends. All right. Then we're going to distribute the electrons to all of the atoms that are in our structure. Okay. We know how many electrons that we have total in like our pool of electrons. And we're going to spread them out to all the atoms, and we're going to try to give everything an octet. All right. If we run out of electrons and we can't give everything an octet with the electrons that we have, that's when we're going to form double bonds or triple bonds. Okay. And at the very end of your structure, you need to go back and check two things every time. You need to check and make sure that the structure that you've drawn has exactly the number of electrons in it that you counted in step one. So those numbers have to match. You also have to check and make sure that every one of your atoms that needs 8 electrons has 8 electrons, unless it's hydrogen, because then it only needs 2 electrons. Okay, so that's a list of rules that you can look at and you can use when you're writing Lewis structures. We're going to look at some examples, and we'll talk through those rules when we look at these examples. Okay, so we're going to look at the Lewis structure for PCl3. Our first rule, we said we're going to count up the total number of electrons that are available for the structure. So we know that phosphorus is in group 5A, so it has 5 valence electrons. We know that chlorine is in group 7A, so it's going to have 7 valence electrons. Right? And there are 3 chlorines. So that means each chlorine has 7 valence electrons. So we're going to multiply that by 3. So those 3 chlorines are bringing in 21 valence electrons total. So now we're going to add those two numbers together. So that means I'm going to have 21 plus 5. I'm going to have 26 valence electrons available for my structure. Okay. Second step, we look at the phosphorus and the chlorine. Once we talk about electronegativity, you'll see that the phosphorus is less electronegative, but we can also use that rule where we see there's 1 phosphorus and there's 3 chlorines. So we're going to put the phosphorus in the middle, and we're going to connect each chlorine to it. Each line that we draw represents a bond, right? And every bond represents 2 electrons. Okay. So now drawing this, we've already used 6 of these electrons. All right. Now we have 20 electrons left out of the 26 we started with. And we're going to try to give everything here an octet. We could start with phosphorus. It has 6 electrons around it right now. So we can add 2 here. Each chlorine is going to need 6 electrons additionally, right? 2, 4, 6, 7, 8. 2, 4, 6, 7, 8. 2, 4, 6, 7, 8. Right? Now everything has an octet. And so now we're going to go to step 5, where we're going to make sure that the number of electrons that we've used matches the number of electrons that we had available to us. Because if those 2 things don't match, we're going to have to go back into step 4, and we're going to have to add double bonds or triple bonds or something to make those numbers the same. But here we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, 26. So that matches. 26 electrons were used. We had 26 electrons available. So that structure is a good structure. Okay. Let's look at a couple more examples. I'm going to put these up here so you could write down the structures for them. And again, pause and try, right? That's the best way to practice. And we can also see what happens when we actually have polyatomic ions as part of our Lewis structure. We'll look and we'll see what happens when we have a negative charge up here or a positive charge up here. Because all it's going to do is it's going to change the total number of electrons in our electron pool. All right, so for ClO4 with a -1 charge, we're going to start the same way that we did last time. We're going to look at the chlorine, and we're going to say, all right, chlorine has 7 valence electrons. Oxygen is in group 6A. So it has 6 valence electrons, but there are 4 oxygens. So we're going to multiply that by 4. So that's going to be 24 valence electrons total. And because there's a negative sign up here, -1, we're going to add these together, and then we're going to add 1 more electron to it. Okay, that -1 means we're going to add 1 more electron to whatever we count up here. So we have 7 plus 24. Okay, 31. And then we're going to add 1 more electron to that. Okay, so we're going to have 32 electrons available. All right, so now we're going to go and we're going to say, all right, how do these atoms connect to each other? We can either look at the electronegativity. Chlorine is less electronegative than oxygen, so it's going to go in the middle. In this formula, though, or in this chemical formula, there's only 1 chlorine and there's 4 oxygens. So we could also use that rule and say, okay, even though it's weird, chlorine doesn't usually like to have more than 1 bond, but there is only 1 chlorine and then there are 4 oxygens that are attached to it. So we're going to connect them like this. Okay. And we're going to remember that each of these lines represents a single bond, which means that these 2 things are sharing 2 electrons. Okay. And now we're going to make sure that everything has 8 electrons. Chlorine already has 8 electrons, so we're not going to worry about that. But each oxygen is going to need 6 more electrons. Okay, and once we give everything 8 electrons, now we're going to count all of the electrons that we've used, and we're going to make sure that it matches this number. And if it doesn't, then we're going to have to make some changes. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Perfect. So we used 32 electrons. 32 electrons used. 32 electrons were available. The only other thing that I have to do to make this structure correct is, because it is a polyatomic ion, I have to put brackets around it. And I just have to put its charge outside. Okay? That's a step that you only have to do with polyatomic ions, just to show that your structure is a polyatomic ion and it has additional electrons in it, not just the valence electrons. All right. That's our first example. Let's look at our carbon monoxide. So we have carbon, we have one carbon, and we have one oxygen that are bonding together. So we know that our carbon is in group 4A, so it's going to have 4 electrons. Oxygen is in group 6A, so it's going to have 6 electrons. So if we add these two together, we're going to have 10 electrons total. That's our electrons available. So now we only have 2 atoms here, so we don't have to worry about making one of them the center. We can just connect our carbon and our oxygen together, right? And they're going to share that bond there. Now, this is going to be a time where we're going to run into one of our multiple bond situations. Because if I try to give everything, each atom that's left, its own octet, watch what happens. So now carbon has 8 electrons around it, and oxygen has 8 electrons around it. But when I look at how many electrons that I've used to make that structure, 2, 4, 6, 8, 10, 12, 14. I've used 14 electrons. I only have 10 electrons available. So when these numbers don't match, that's when you know that you have to add a double bond or a triple bond. And so what you're going to do is you're going to look back at your structure and you're going to say, okay, I'm going to reduce the number of electrons that I'm going to use by having my atoms, like instead of carbon having its own pair and oxygen having its own pair up there, instead they can share one pair. So instead of each having their own and using 2 pairs, they'll take a pair and they'll just share them. So now if I count up how many electrons I've used, it's 2, 4, 6, 8, 10, 12. So I've reduced the number of electrons that I've used to make my structure. I haven't reduced it enough yet because I still am using too many electrons. But now I can look back at this and say, all right, well, instead of carbon having its own pair and oxygen having its own pair here, they'll just share one pair. They'll share one more pair. And so now there's 2, 4, 6 electrons, 8, 10. So now my structure is only using 10 electrons, and I see that there is a triple bond between my carbon and my oxygen. But I know that I had to use a triple bond, or I knew I had to use a multiple bond. You don't have to like decide right away whether it's a double bond or a triple bond, but you'll know you have to use a multiple bond when the number of electrons that you've used for your structure is more than the electrons that you have available to you. Okay. Let's try our next example. This is going to have hydrogen in it, carbon in it, and oxygen in it. Each hydrogen has 1 valence electron, and there are 2 of them, so we'll multiply that by 2. Each carbon has 4 valence electrons, and there's only 1 of them, so we'll just write 4 so we can make a little sum line. And oxygen has 6 valence electrons, so that'll have 6. So when we add those all together, 6, 10, we have 12 electrons available to us. Okay. In this structure, this is one of the times when looking at it and recognizing that carbon is the least electronegative atom that's present will be helpful. Um, but also, if you have carbon in your compound, if you ever have just carbon in your compound, carbon is probably going to be the central atom. Carbon loves being the central atom. So in something like this where you see that carbon present, you can be very comfortable putting carbon as your center. And then we're just going to attach the other things to it. So we can attach, doesn't matter the position, you just have to attach two hydrogens and an oxygen. Doesn't matter your layout here. Each line that you draw is going to represent a bond, two electrons, and then you're going to give everything else an octet, except for hydrogen, which only needs the two electrons that you've already given it. But carbon has 6 electrons around it, and it wants 8. Oxygen has 2 electrons, and it also wants 8. When we draw this out, we'll count our electrons now that we've used. 2, 4, 6, 8, 10, 12, 14. We've used 14 electrons. We have 12 electrons available. So that again tells us, well, we're going to need a multiple bond here. And so what we're going to do is we're going to look at the carbon, the lone pair that's on carbon, and we're going to look at one of the lone pairs on the oxygen. Doesn't matter which one. And we're going to say, instead of each of you having your own lone pair, you guys are going to share a pair. And we're going to put that shared pair between them. And now we have 2, 4, 6, 8, 10, 12 electrons that we've used. And now our structure is correct. Okay. Our last ion that we'll look at here, this is a positively charged polyatomic ion, just so we could see what happens on the other end of this. We're going to start off the same way. We'll count up our nitrogen, has 5 valence electrons. Our hydrogens have 1 valence electron, but there are 4 of them, so we're going to have 4 electrons total. So if we add these together, we're going to have 9 valence electrons. That positive 1 charge means that we're going to remove an electron. Remember, when things get more positive, they're losing electrons. So if this is a +1 charge, then we're going to take 1 electron away from this total. If that was a +2 charge, we'd take 2 electrons away from that total. Okay? But we only have a positive 1 charge here, so we're going to remove 1 electron from that total number, and we're going to have 8 electrons available to us. Okay, so we're going to put the nitrogen in the middle. We're going to connect it to the 4 hydrogens. Each of those bonds represents 2 electrons, and we see that we've used 2, 4, 6, 8 electrons. So that's exactly as many as we had, so that means our structure is good. Because it's a polyatomic ion, we're going to bracket it off, and we're going to put that +1 charge on the outside. Okay? So that is how we write our Lewis structures. The next thing that we're going to talk about is actually the electronegativity that I've mentioned a couple times. Electronegativity is helpful. It helps us kind of figure out what's happening with the electrons and with kind of how fairly the electrons are being distributed in any structure. We need to know what the term electronegativity really means before we can talk about it. The definition of electronegativity is an atom's ability to attract shared electrons in a chemical bond to itself. That's kind of the way I like to think about electronegativity. It's like a pull. Like which element is strong enough to pull the electrons towards itself. And whichever element can pull the electrons towards itself more is going to be the more electronegative element. We can figure out electronegativity from looking at the periodic table because there's a trend on the periodic table that reflects the general electronegativity values. In general, your nonmetals will have higher electronegativities than your metals will. Your fluorine in the top right of your periodic table, that's going to have the highest electronegativity. Your electronegativity for metals overall is very low, and your lowest electronegativities are going to be down in the bottom left of your periodic table. This is an overall view. This is like a squished in view of the periodic table. They're leaving out the middle bits with the transition metals here because there's no real change in the trend with your transition metals. But you'll notice that as you go from the left side of the periodic table to the right side of the periodic table, lithium is a metal. It has an electronegativity of 1. Fluorine has an electronegativity of 4. So fluorine, way more electronegative. When you look down a column, lithium has an electronegativity of 1, and cesium only has an electronegativity of 0.7. So cesium is way less electronegative than lithium. Fluorine is way more electronegative than your astatine, which is down at the bottom of that same column. So we see that up in the top right, this is going to be your highest electronegativity. And in your bottom left, this is going to be your lowest electronegativity. So you can use those trend lines to help you figure out what is more or less electronegative when you're trying to put together like your Lewis structures, for example, or when you're trying to look at a bond and you're trying to decide whether one atom is hogging the electrons from the other, because that's really what happens inside of bonds. And that's what we're going to talk about next. We're going to talk about bond polarity. If there is a difference in the way that two atoms are sharing the electrons, we're going to consider that bond to be a polar bond. A polar bond means that there's going to be two distinct poles to your molecule. There's going to be a positive pole and a negative pole. So if we look at two examples here, the first picture that they've given us here are two hydrogen atoms that are coming together to form a hydrogen molecule. Hydrogen has the same electronegativity as itself, right? There's no difference in electronegativity between one hydrogen atom and another. So when these two things come together, they're going to have a perfect sharing of these electrons. They're equal, completely equal. Nope, there's not going to be one hydrogen that pulls the electrons towards itself more than another hydrogen. That type of bond is called a non-polar covalent bond because there are no positive and negative poles here. There's no charge that's distributed across that bond. Everything's equal. If you have hydrogen and chlorine coming together to form a bond, the chlorine is way more electronegative. And so the chlorine is going to actually pull the electron that hydrogen is offering to share. It's going to pull it a lot closer to itself. And so in your molecule, you're going to end up with a lot of the negativity centered around the chlorine, and hydrogen is going to be left pretty positive. Okay. And you can see the charge difference here with these symbols. You're going to have that little scripty symbol there with a positive charge. That means you have a partial positive charge by your hydrogen. And then this means you have a partial negative charge by your chlorine. Okay. But let's look at how we figure out whether or not we have a difference in polarity. We can use the electronegativity values from the table that we were just looking at to assign like a individual electronegativity values. And once we know the individual electronegativity values, we're going to classify them based on their electronegativity difference. So if you have two nitrogen atoms, for example, each nitrogen has an assigned electronegativity value of 3. Okay, that doesn't come from, that's not random, that comes from the table. So each nitrogen is a 3. So now if we have two nitrogens that are bonding together, each has an electronegativity of 3. The difference between those is 0. So it's a nonpolar covalent bond. When you have two atoms that are the same, the bond will always be nonpolar covalent. When you have two atoms that are different from each other, You have to look at their electronegativities to decide whether they're polar or nonpolar. Okay. And you don't have to have these values memorized. If you need to use these values, then the electronegativity values will be given to you either in the question or as a table that's part of the question for you to use. But for the example that we were just looking at, we're looking at the bond between bromine and chlorine. So bromine has an electronegativity of 2.8. Chlorine is a 3.0. So when I look at that bond that's forming and I look at the two electronegativities, I see that there's a 0.2 difference between them. When you look at the electronegativity difference, any electronegativity difference between 0 and 0.4 is going to be considered a nonpolar covalent bond. Okay? So that means we're going to have equal or almost equal sharing of electrons. All right? When we have electronegativity differences that get a little bit higher, so if you have an electronegativity difference of 0.5, 0.6, 0.7, 1.0, this means that the sharing of the electrons is not equal anymore. And so now we're going to have a pole that emerges, two poles on your compound, positive pole and a negative pole. And that type of compound or that type of bond is called a polar covalent bond. When you have a polar bond form, you are going to want to be able to write it as what's called a dipole form. Okay. This is when you represent your bond. So you can represent the two atoms, and you're going to put your positive symbol by the more positive one, the one that has the lower electronegativity. And you're going to put your negative symbol by the element that has the higher electronegativity value. Okay. You're also going to draw an arrow, and that arrow is going to have the arrowhead move towards the more negative side because the electrons are moving towards the more negative side. And then you'll put the tail of the arrow by the more positive side. And you see when you draw it, it kind of makes it look like a plus sign, and it should be by the more positive side. Okay. When you have electronegativity values in your bonds that are larger than 1.8, your bonds are no longer covalent. In that case, you're going to have ionic bonds forming. So you'll see if you're looking at chlorine and potassium, and this should make sense to you, right? Because we said when metals and nonmetals form bonds, those bonds are ionic bonds. Well, potassium is a metal, chlorine is a nonmetal. When we look at chlorine's electronegativity, it's 3. Potassium is only 0.8. So the electronegativity difference between them is 2.2. Any electronegativity difference that's higher than 1.8 is going to result in an ionic bond. All right. So this is a summary from that chart, and you do need to know these classifications. Okay. So 0 to 0.4, your bond would be nonpolar covalent. From 0.5 to 1.8, your bond is going to be polar covalent. And if it's greater than 1.8, your bond is going to be ionic. And when you have a polar covalent bond, you should be able to sketch the dipole out. So you should be able to sketch the arrow and include your positive and negative symbols. All right. This is just a visualization of that same information. Right. So let's look at some examples here. So use the electronegativity differences. You can look at your table for this to identify the type of bond between the following. All right. We're going to have NP for nonpolar covalent. We're going to have P for polar covalent. And we're going to have I for ionic. And when you have a polar covalent bond, I want you to write out the symbol, the positive, negative symbol, and the arrows. Okay. So, if you're working along with me here, then pause it here and try it on your own. And then we'll talk through it. All right, we'll go back um, in our notes to find the electronegativity values of everything that's here. When you're finding the electronegativity difference and you're doing the subtraction, you can always subtract like the bigger number minus the smaller number because you don't need to, you're just looking for an absolute value when you're looking at the difference between the two of them. Um, so here, when I look at this difference, it's going to be 3.0 minus 0.8. So that's going to be a difference of 2.2. That's going to be an ionic bond, which makes sense because it's a metal and a non-metal. With N and O, I'm going to have 3.5 minus 3.0. That's a difference of 0.5. So this is going to be polar covalent. We'll sketch that out in a second. 3.0 and 3.0, those are the same. That's automatically non-polar covalent. And then 2.1 and 3.0 is an electronegativity difference of 0.9, and that is going to be polar covalent. So for our polar ones, we can write out the bond. We're going to put our positive symbol over the less electronegative atom, and we're going to put our negative symbol over the more electronegative atom. And then we're going to draw our arrow so that it goes towards our more negative atom, and we'll put our little vertical line by the more positive one. And then down here, HCl. So our hydrogen is going to be more positive, our chlorine is going to be more negative, and then our arrow is going to go towards the chlorine because it's more negative, and our hydrogen gets our little vertical line. Okay. All right. The next thing that we are going to look at is the shapes of our molecules. Okay. We're going to look at the shapes, and then we're going to look at the polarity of our molecules overall, not just the polarity of the bonds within the molecules. So we're going to have to use our Lewis structures for this part, and we're going to have to use our understanding of bond polarity here. And what we're going to see is that the shapes of our molecules are important because the structures are going to affect the properties of our different molecules. Okay. There's something called valence shell electron repulsion theory, VSEPR theory, that is going to describe the orientation of electron groups around your central atom. So it's going to describe how the electrons position themselves around that central atom that is holding all of our bonds together. And VSEPR theory states that electron groups are always going to try to arrange themselves as far from one another as possible because electrons are negative. So they want to stay away from each other and spread out. And then we're going to see that the specific shape of our molecule is going to be determined by how many electron groups there are and kind of like how many bonds versus lone pairs there are. But we'll take a look at what that means in a second. So this is a visualization of the VSEPR theory. Your electron groups, like you have to imagine that each of these are a pair of electrons. So that's going to be an electron group. And there's repulsion, right? And so they're not going to want to be near another electron group unless they have to be. So all of those repulsions from the negative charges being near each other, that's what keeps these things as far apart as possible. When we draw out our Lewis structures, we've already kind of seen this in the structures we've drawn out. We're going to have bonding pairs, which are going to be the pairs of electrons that form the bonds between our atoms. And we're going to have lone pairs, which are going to be the unshared electrons that just sit on the atom by themselves, and they're not being shared by anything else. Okay, bonding pairs and lone pairs. You want to have an idea of what each of those terms means for the rest of this to make sense. When we draw out our Lewis structures, before we can figure out the shape of our molecules, we're going to count the number of electron groups around our central atoms. Okay. To do this, we're going to draw out our Lewis structure. And when we draw it out, we are going to look at each lone pair of electrons that's present on our central atom. And each lone pair of electrons is going to count as one electron group. Okay. Then we're going to look at each bond that forms, right? So this is a single bond. This is a double bond. Each electron bond, regardless of whether it's a single bond, a double bond, or a triple bond, each type of electron bond counts as one electron group on that central atom. And when we're counting electron groups for our Lewis structures, we are only counting electron groups around the central atom. Okay? The central atom only. We don't worry about the oxygens. We only worry about what's happening with our central atom, our nitrogen. So if we were looking at this Lewis structure, we would determine that there are 3 electron groups around the nitrogen because we have 1 electron group from our lone pair right here. We have 1 electron group from that single bond, and we have 1 electron group from the double bond. Okay, so that's 3 electron groups total. All right. Now we're doing this because electron groups are going to determine the shape of our molecule. And the initial shape of our molecule is called electron geometry. Electron geometry is the 3-dimensional arrangement of your atoms around a molecule. How much do they spread out? We're going to be looking at molecules that have a maximum of 4 electron bonding groups around their central atom. There are more than that, but we're going to focus on a maximum of 4 bonding electron groups in the middle. Each of these arrangements is going to give us a maximum of 3 basic electron geometries that we have to know. And electron geometries, these are like the perfect geometries. This means that everything is equal. Everything is being shared equally. Everything is spread out perfectly from each other. There are 3 of these electron geometries that we need to know. But electron geometries aren't the only type of geometries that we have to be familiar with. There's molecular geometries, or the actual shape of our molecules, that we have to take into consideration. The shape of our molecules is going to be affected by the number of electron groups, for sure, but also by what type of electron groups we're looking at. Molecules that have lone pairs in them are going to have slightly different shapes than molecules that only have bonds. All right? Molecules that have lone pairs, we don't necessarily see those lone pairs when we draw out when we like look at the structure of the molecules. We don't always see the lone pairs, but their effect we see because they still take up space on our central atom. So they're still going to affect the shape that our bonds take. All right, we'll be able to see this a little more. I'll pull out the molecule kits in a second to get a look at this. These are our 3 perfect electron geometries. If we have 2 electron groups around our central atom, this is called a linear geometry because our electron groups spread out from each other 180 degrees. They make a perfect line to get as far away from each other as possible. Notice that for each of these electron geometries, they're going to only contain bonds as electron groups. There are no lone pairs in these electron geometries. When we have 3 electron groups and they spread out perfectly from each other, it's like taking a circle and dividing it into thirds perfectly. And we'll see that each bond is exactly 120 degrees from the next bond, right? So if we add all those together, it's 360 degrees. Perfect circle there. When we have 4 electron groups, the bonding groups are going to spread out from each other in 360-degree space. So it's like taking a sphere, okay? And we're taking a sphere and we're spreading those bonds out in 3 dimensions. Every bond is going to be able to be 109.5 degrees from the next bond. So each of these bond angles that we're looking at is 109.5 degrees from the other. Those are our 3 categories: 2 electron groups, 3 electron groups, 4 electron groups. So we either have a linear electron geometry, a trigonal planar electron geometry, or a tetrahedral electron geometry. And the type of electron geometry we have is going to be determined 100% by the number of electron groups that are around our central atom. Okay? So let's look at each one individually and we'll see what happens when bonding pairs are replaced with lone pairs, because that's going to change our shape just a little bit. But let me go grab my little models. All right, so when we have central atoms that have 2 electron groups, the electron groups are going to occupy positions on opposite sides of the atom. These types of molecules, we're going to say they have a linear electron geometry and a linear molecular geometry as well. Okay, so the electron geometry and the molecular shape, or the molecular geometry, those are the same for any atom that has 2 electron groups around your central atom. So remember what we're looking at here. This is your Lewis structure. Carbon is your central. You've got 1 electron group here with this double bond. You have 1 electron group here with this double bond. And so that's how you know that it's going to be linear. When you have 3 electron groups, there's going to be 2 possibilities for the shape that your molecule takes. If you have something that only has 3 bonding groups around it, so something like we actually drew out the Lewis structure for this earlier. We have a single bond here, a single bond here, and a double bond here. So that's 3 electron groups. The electron geometry for this is trigonal planar. Okay, and it's called trigonal planar because your molecules, if we look at this real quick, your molecules, all right, let me just find, all right, this will work. That looks a little bit better than putting it on the whiteboard. They're in one plane, okay? So that's why it's called planar, and it gets the trig because there's 3 of these things, right? So there's 3 sections that are being divided up into the same plane. And the bond angles here are the 120 degrees that we see. Okay, so anything that has 3 electron groups is going to have a trigonal planar electron geometry. When you have 3 bonding groups and you have no lone pairs, then your molecular shape is the same as your electron geometry. All right, whenever you have 0 lone pairs around your central atom, your electron shape, your electron geometry rather, and your molecular shape are the same geometry. They're the same. It's when one of your bonding groups gets replaced by a lone pair. So let's replace this. We'll use this to represent a lone pair. So when one of your bonding groups gets replaced by a lone pair, this is when you're going to have a molecular shape that's different from your electron geometry. Okay. This shape that forms is called a bent molecular shape. Bent. All right. The bond angles here are going to be a little bit less than 120 degrees because these are pushing in a little bit closer because the lone pair is so negative, but they're still going to be pretty close to 120 degrees. Let me show you the slide for that one. Okay, so when we have 3 electron groups that are all bonding pairs, we're going to have a trigonal planar electron geometry and a trigonal planar shape. When we have one of our electron groups replaced by a lone pair instead of a bonding pair, then we're going to have a trigonal planar electron geometry still, but we're going to have a bent molecular shape. All right. And then we have our atoms, our molecules rather, that have 4 electron groups around them. These are going to start off when you have only bonding groups, 0 lone pairs. Your electron groups are going to take a tetrahedral electron geometry and a tetrahedral molecular geometry. Whenever there are 0 lone pairs, your electron geometry and your molecular shape are the same. Okay? And your bond angle here is going to be 109.5 degrees. There are 2 variations to the shape when you have 4 electron groups. First variation, I'll look at the slide first and then I'll show you what it looks like in the molecule. When one of your electron groups is replaced by a lone pair, the shape changes from tetrahedral to trigonal pyramidal. Okay, this is when you're going to have 3 bonds and 1 lone pair. So you're going to have a trigonal pyramidal molecular shape, but your electron geometry is still tetrahedral. Okay. The bond angle will be a little bit less than 109 degrees, but it's going to be pretty close to that still. And what that looks like, it would be like if you started out with this molecule here. Okay, so you see in 3-dimensional space how everything is spread out. Now we're going to take one of these bonding groups and we're going to replace it with one of those, imagine a lone pair up here. Okay. And now what it forms is a little pyramid, right? You see how there's space there? Like it's not sitting flat. There's room underneath it. So it's a pyramid, and it's a pyramid that has 3 legs. So that's why it's called a trigonal pyramidal, because it's a 3-legged pyramid that forms. Okay. That's what happens when we have one bonding group replaced by a lone pair. The final shape that we have to look at is when we have 2 bonding groups that are replaced by lone pairs. And when that happens, we're going to end up with another shape that is also called bent, like the trigonal planar. I find it helpful to differentiate them a little bit. Like for this one, I would call it bent 109, just to represent that it's part of our tetrahedral electron geometry. So the bond angles are going to be a little bit closer to 109 degrees. But when you have a molecule that has 4 electron groups and 2 of those electron groups are bonds and 2 of those electron groups are lone pairs, then your shape is going to be a bent shape, but your electron geometry is still tetrahedral. Okay. So again, one more time with the sharing here. If I take this molecule, I've already removed one of the electron groups, but if I remove another, now what happens, right? It looks real similar to that bent molecule that we made before, right? Looks real similar to this. The only thing that's going to be different is going to be the bond angles here. Bond angle for this one is going to be 109.5. The bond angle for this one is going to be 120. Okay. And those are our shapes. And if you look at your table, share my screen again, the table from your textbook and from your notes, you can use that table to help you figure out the shapes until you get to know the table better. And then you'll be able to figure it out. Kind of, there's only a few different shapes to really know. What I would suggest though is kind of being able to recreate this table for yourself a little bit. Okay. So notice that when you have 2 electron groups, there's only one possible geometry. When there's 3 electron groups, there's going to be 2 different types of geometries or shapes. When there's 3 electron groups, there's going to be 3 different shapes. Your electron geometries, they're only dependent on the number of electron groups. So when you have 3 electron groups, the electron geometry stays the same, but the shape changes. When you have 4 electron groups, the electron geometry stays the same, but the shape changes. Okay. So what I'd recommend is being able to sketch this out for yourself and do it like in a flow chart way. So that, because then it makes it easier. You're not just trying to like memorize writing down a chart. So you'll say, all right, if I have 2 electron groups, then your electron geometry, we'll make a section here for electron geometry. And then we'll make a column here for molecular geometry. Okay, so if I have 2 electron groups, my electron geometry is linear. And my molecular geometry is always going to be linear as well. When I have 2 electron groups, linear is the only option. When I have 3 electron groups, my electron geometry is always going to be trigonoplanar. But I have 2 possibilities for my shape that happen. I'm going to have one possibility where I have 0 lone pairs. And I'm going to have one possibility when I have 1 lone pair. Okay. When I have 0 lone pairs, then my electron geometry and my molecular geometry or shape, your textbook uses shape more than geometry. So we'll just write shape there. When I have 0 lone pairs, my shape is going to be the same as my electron geometry, and it's going to be trigonoplanar. When I have 1 lone pair, my shape is going to change to bent. And then you can put the 120 there for trigonoplanar. When I have 4 electron groups, I'm going to have 3 possibilities. But first of all, for my electron geometry, if it's 4 electron groups, then the electron geometry is always tetrahedral. But in terms of my shape, this is when I'm going to have my possibilities. I'm either going to have 0 lone pairs, or I'm going to have 1 lone pair, or I'm going to have 2 lone pairs. And if I have 0 lone pairs, then my molecular shape is going to stay tetrahedral. Oh, let's put an equal sign there like that. If I have 1 lone pair, then my shape is going to change from tetrahedral into trigonal pyramidal. And if I have 2 lone pairs, my shape is going to change to bent, but this time 109. Okay. It's not that hard to like to set up that chart for yourself. And if you can kind of write out that flow chart, it's going to be easier to pick out the different geometries. And you have to be mindful whether someone's asking you to report the electron geometry or the molecular geometry or shape, because those 2 things can be different answers depending on whether there are lone pairs present around your central atom. Okay. Let's look at a few examples from the slides. They give us 4 different examples to try. All right, so we're going to look at H2S. We're going to look at PF3. We're going to look at H2O and then CCl4. And for each of these, you start by drawing out the Lewis structure. And then once you have the Lewis structure, you count your electron groups. Okay. So for sulfur, remember when we said we had our simpler molecules, you probably can figure out the Lewis structures a little bit easier from these. We know that sulfur has 6 valence electrons. Each hydrogen is contributing 1 valence electron. So when we set up our Lewis symbol for sulfur and we set up our hydrogen right next to it, we know that this is how the bonds are going to form, right? When we look at that Lewis structure, we're going to count our electron groups. 1, 2, 3, 4 electron groups. 4 electron groups means that our electron geometry, we'll abbreviate it as EG for electron geometry, is going to be tetrahedral. But we have 2 lone pairs. So our shape is going to be bent. Okay. For our second one, we have phosphorus with its 5 valence electrons in the middle, and we have 3 fluorines around it. Doesn't matter how you draw this. Each fluorine is going to have 7 valence electrons, and there are 3 of them. That's 21 total. So that means that we're going to have 26 electrons available for our structure. And we've actually sketched this one already. So if you wanted to go back and look at that, you could. Each fluorine will get its additional electrons. Phosphorus gets its additional electrons. And we see that we've used 8, 16, 24, 25, 26 electrons, which is perfect. That's what we wanted to use. Now, when we count the number of electron groups, we're only going to focus on our central atom. 1, 2, 3, 4 electron groups. So we're still going to have an electron geometry that's tetrahedral. But in this case, we're only going to have 1 lone pair. And so that means that our shape is going to be trigonal pyramidal. Okay. For our H2O, we're going to have an oxygen that has 6 valence electrons around it, and then a hydrogen on each side. The shapes of these 2 things should hopefully look very similar to you. We have 4 electron groups around it. And we have 2 lone pairs. Which means that our shape is going to be bent. 109 specifically, just like this was bent, 109. And then for our last one, we have CCl4. We have our carbon in the middle. It's going to be surrounded by 4 chlorines. When we look at our structure, we know that carbon has 4 valence electrons. Each chlorine has 7, and there are 4 of them, which is 28 total. So if we add all of our electrons together, we know that our structure should have 32 electrons in it. And if we count this up, 8, 16, 24, 32. So we know that our structure is good. We look at the electron groups around our central atom. we're again looking at 4 electron groups. Each of these examples were examples of tetrahedral electron geometry. This time we have 0 lone pairs. And so our shape is going to stay tetrahedral. Okay. Let's take a look at how we look at the polarity of molecules. Okay, because now we've got the shape of them. We know how to find the polarity of bonds. So now we can look at the polarity of molecules. We're going to have the same options for molecules as we had for bonds. We're going to have either nonpolar molecules, polar molecules, or ionic compounds if we have ionic bonds forming. Okay. When we have molecules that are made up only of nonpolar bonds, then these molecules will also be nonpolar. All right. But we can have molecules that have polar bonds in them that turn out to be nonpolar if the bonds are arranged symmetrically. So, like something like carbon dioxide. The carbon oxygen bond is polar, but we have a carbon oxygen bond on either side of the carbon exactly opposite each other. So if you imagine it like a tug of war, neither oxygen can win because they're both pulling the exact same amount on the electrons. So the electrons just kind of stay evenly distributed. The same thing happens in CCl4. The carbon chlorine bond is polar, but you have an even pulling from all of the chlorines. And so no chlorine ends up with more electrons than any other chlorine, right? So when we have symmetry in our shape, when you have something that's linear or you have something that's tetrahedral, that symmetry coupled with polar bonds will still leave you with a nonpolar molecule because the polar bonds will cancel each other out in the process. Polar molecules are going to happen when you have polar bonds that don't end up being canceled out by the shape of the molecule. Okay. When you have a single bond, that 2 atoms with a single bond and that bond is polar, there is no cancellation. So the molecule automatically ends up being polar, right? So in this case, the chlorine ends up being very negative, the hydrogen ends up being very positive. And something like H2O, the hydrogen oxygen bond is a polar bond, but the shape of H2O is a bent shape, right? So it's not like a tug of war that's equal like the carbon dioxide. In this case, the hydrogens are not opposite each other. They're kind of pushed together because they have these lone pairs up here. It is very likely that in the molecules that you are going to be looking at, that if your structure has a central atom with lone pairs of electrons, that molecule will be a polar molecule because it is very hard to cancel out the negativity of those lone pairs of electrons. So in this case, this oxygen is going to be our more negative end of the part of the molecule because the oxygen is more electronegative. So it's going to be pulling the electrons from the hydrogen. And the oxygen itself also has 2 lone pairs of electrons around it. All right, the same is true with our NH3 molecule. You'll notice that lone pair of electrons up here. This is a trigonal pyramidal shape. So the nitrogen is going to be pulling the electrons of all the hydrogens towards itself. And in addition, it has its own pair of electrons up here. So the nitrogen is going to be very negative and the hydrogens are going to be pretty positive. So when you're trying to figure out the polarity of a molecule, you're going to go through like a 2-step process. You're going to look to see if the bonds are polar covalent or non-polar covalent. If all the bonds are non-polar, then your molecule is non-polar anyway. But if the bonds are polar covalent, then you're going to draw the Lewis structure and you're going to figure out if the dipoles cancel out or not. Okay. So we'll just look at a couple of examples of this. So we've got OF2. What other examples did we give us? PBr3, HBr, and CH4. All right, so for OF2, we'll start by drawing out, well, I mean, you could start two ways. You could look at the Lewis structure or you can look at the bonds. The Lewis structures aren't difficult to write out for these ones. We know our oxygen is going to go in the middle because there's one of them. It's also less electronegative than fluorine. You'll have a fluorine on each side. And then when we look at the electronegativity difference between oxygen and fluorine, this is something you can look back in your table for. You don't have to have these numbers memorized. But if you're expected to do this kind of like calculation on an exam, they give you the numbers. If they didn't give you the numbers, you should still be able to look at oxygen and fluorine and know based on the trend that fluorine is more electronegative than oxygen and that this would still be a polar bond. You don't need the numbers to show you that. You can prove it with the numbers, but you can just look at the two atoms' position on the periodic table and know that anything that's bonded to fluorine that's not fluorine itself is going to be a polar bond because fluorine is more electronegative than anything else on your periodic table. But we can show it numerically with the numbers. This is 3.5, this is 4.0. The electronegativity difference between them is going to be 0.5, which means it's polar. And now you're going to have to look at the shape of this to see if the bonds cancel out. When you sketch it out like this, it's very misleading because this looks like it could have a linear shape and it looks like it could cancel out the way that it's sketched here. That's why it's so important to understand the shape, the geometries that we were talking about. Because knowing the geometries now, we can look at this and we can say there are 4 electron groups around it. So it's going to have a tetrahedral electron geometry. 1, 2, 3, 4 electron groups. When we had 4 electron groups and we had 2 lone pairs, the shape of that was a bent molecule. And that means that what this would actually look like is our oxygen with 2 fluorines, and then we'd have these lone pairs up here. That's not symmetrical. Okay? That means that in this molecule, we would definitely still have 2 different poles, positive and negative end. All right? So this is going to be polar. No symmetry. And it had polar bonds. Okay, our next example, PBr3. Draw out the Lewis structure for this. Okay, again, we've seen like PF3 and PBr3, we've seen a few times. For this one, we have 4 electron groups. And we have 1 lone pair. That combination means that we're going to have a trigonal pyramidal shape. If we have a trigonal pyramidal shape with this lone pair of electrons here, that is not symmetrical. That means that we are going to have a charge difference across the molecule. When you have a lone pair of electrons there, when you have a lone pair of electrons here, we can't have a nonpolar molecule. Those lone pairs of electrons they have more negativity in them than any of the bonds. Okay. This is going to be polar, no symmetry again. Just shorten that up a little bit. For our HBr, this is linear. Hydrogen has an electronegativity of 2.1. Bromine is way more electronegative. It's going to be a polar, but I want to get the number for you. Again, this is one that you should be able to tell just by positioning on the periodic table. It's hydrogen and then this halogen in group 7. So you know there's going to be an electronegativity difference. The difference is 0.7. So it's definitely polar. It's a molecule that only has one bond in it. If the bond is polar, that means that the molecule is polar as well. Okay. So this is going to be polar. For our CH4 molecule, which looks like this. You can look at this two ways. Say that you could look at the carbon-hydrogen bond. Carbon is 2.5 electronegativity. Hydrogen is 2.1. So you could look at that bond and say, oh, the bond is a nonpolar bond, so it's not going to be a polar molecule. There's no lone pairs around it. So there's nothing to make it polar. But even if you didn't know these numbers, you could look at that structure and you could say this is a tetrahedral shape. Each of these bonds has the same exact electronegativity and there are no lone pairs. So that means that no hydrogen is going to pull the electrons towards itself, or carbon's not going to be able to pull any hydrogen's electrons towards itself more than any other. And because there's going to be no pool of positivity or no pooling negativity anywhere, it's going to make your molecule nonpolar overall. So this is going to be nonpolar. And some reasons that we can give for that are that we have no lone pairs. The bonds themselves are nonpolar. And all of the terminal atoms are the same. So they're all going to have the same amount of electronegativity pull towards the carbon. Okay, so those are our polar versus nonpolar. All right, the last section of this chapter that we want to cover has to do with intermolecular forces. We needed to know about molecule polarity before we could talk about intermolecular forces. Intermolecular forces they're not bonds. They're not real bonds that are forming between different things. They're attractions between different molecules. So for example, when you have something like a water molecule where the water is very negative and the hydrogens are very positive, if you have two water molecules that are next to each other, the positive hydrogens might get real close to the very negative oxygens, and there's an attraction between the positive and negative charges here. That attractive force is called an intermolecular force. And there's different types of intermolecular forces. This specific one is called a hydrogen bond, even though the force itself is not a bond. But this is an intermolecular force. So we're going to talk about the 3 different types of intermolecular forces and what their effect would be on different types of properties. So what we're going to see is that the strength of the different intermolecular forces is going to, first of all, determine the physical state of different material at different temperatures. So if we're looking at like regular room temperature, things that have very strong intermolecular forces or even medium intermolecular forces will most likely be solids or liquids at room temperature because their molecules are being held together in that solid or liquid state longer. When you have stronger intermolecular forces or stronger attractive forces, it's harder to convert into a gas phase, okay? Because gases mean that you separate apart and then you move really far away from each other. So we're going to see that the stronger the attractive forces are, the higher the boiling points of liquids would be, and the higher the melting points of solids would be. These are our three kinds of intermolecular forces or attractive forces. We're going to have dispersion forces, which every substance has. These are temporary poles that form in molecules because of unequal electron distribution. Dispersion forces are very, very weak forces. And you'll see these temporary dipoles like form and then unform and then reform, even when you have nonpolar molecules present. Then we're going to have dipole-dipole attractions. These are when you have polar molecules together. And then we're going to have hydrogen bonding, which is really just a super strong dipole-dipole force, but it's a dipole-dipole force in molecules that specifically have hydrogen attached to a fluorine, oxygen, or nitrogen. That's where the term hydrogen bonding comes from. So we're just going to look at these one at a time. Our dispersion forces are going to be really weak attractions between nonpolar molecules. The forces come from these temporary dipoles that happen when you have molecules bumping into each other and electrons moving around. You'll have moments in time where the electrons from one atom get very close to the nucleus of another atom. And when that happens, that's when you can have a dispersion force form because you're like, oh, this is all my negativity and that's all my positivity. And then you get a very brief moment in time where there's a attraction between them. This is the only type of intermolecular force that nonpolar molecules can have. Okay. Every single molecule has dispersion forces, but this is the only type of force that something that's nonpolar can have. It is the weakest intermolecular force. All right. What we see with our dispersion forces is that they are going to generally increase in strength as the molar mass of a substance increases. And as the dispersion force gets stronger, our boiling point is going to increase along with it. So we could just look here at the correlation between molar mass and boiling point in these noble gases, which are all nonpolar. And as the molar mass increases, the boiling point increases as well. In our polar molecules, we're going to have dipole-dipole forces. Our polar molecules are going to create a permanent dipole within the molecule, like we just saw with HCl, for example. The hydrogen is always going to be super positive and the chlorine is going to be super negative. And so if you have two HCls that are next to each other, when the chlorine from one of them is next to the hydrogen from a second, the attractive force between the hydrogen and the chlorine, this is not going to form a bond, but it's going to form an attraction. Think about intermolecular forces like a series of magnets. Your dispersion forces are a very weak magnet. They'd be like the type of magnet where if you put it on a refrigerator, it would just like slide down the refrigerator because it was so weak. There's still a little bit of attraction there, but it's not very strong. Your dipole-dipole forces, these are like regular magnets. You stick them together and they attach, right? Or you stick the magnet to the fridge, it attaches. And it's not like it's permanent. You can always pull it back off, but it's still, sticky in that moment. That's what an intermolecular force is. It's sticky in that moment, but then you could still pull it apart. But the dipole-dipole force is going to be stronger than the dispersion force. So polar molecules in general are going to have higher melting points and boiling points than nonpolar molecules of a similar size. And then there's going to be hydrogen bonding, which is the strongest of these intermolecular forces. And it is just a very, very super strong dipole-dipole force. A hydrogen bonding attractive forces would be like if you had just a super strong magnet that you had to pull really hard on before you could get it apart. Okay. Um, the These happen when you have hydrogen attached to your most electronegative atoms, specifically fluorine, oxygen, nitrogen. Um, you'll see like an example here is water molecules. We looked at this already, the oxygen and the hydrogen, the oxygen and the hydrogen, and the hydrogen bonding or the super strong dipole-dipole force happens between the hydrogen of one molecule and the oxygen from another molecule. Same thing happens with ammonia because you have a hydrogen attached to a nitrogen. And so the hydrogen from one molecule gets close to the nitrogen of a second molecule. And this is where our hydrogen bonding occurs. These are going to be the strongest intermolecular forces between molecules. Hydrogen bonding has a huge role in the shape that DNA takes, that helical structure. But just remember that hydrogen bonds are not real bonds. They're just extremely strong attractive forces. Okay. So these are our summary of our intermolecular forces. We have our dispersion forces here. All atoms have them. They're the only ones that non-polar molecules can have, rather. We have our dipole-dipole forces, which our polar molecules are going to have. And then we're going to have hydrogen bonding, which are polar molecules that contain a hydrogen bonded to a fluorine, oxygen, or nitrogen are going to have. Okay. And this is the weakest, and the hydrogen bonding is the strongest. In terms of melting points and boiling points, we're going to see that the melting points and boiling points are related to the strength of the intermolecular forces between our molecules and our compounds. So we're going to see the lowest in the dispersion forces. We're going to see much higher melting points and boiling points in our compounds that have, or molecules that have hydrogen bonding. But we're going to see even higher melting points and boiling points with ionic compounds because the ionic compounds have real ionic bonds between them. These are going to take a lot more energy to break apart than an intermolecular force. Okay. So this is just an overall table kind of giving you that idea. Our weakest are down here with our dispersion forces. Our strongest are up here with our ionic bonds. Covalent bonds are just slightly less strong than ionic bonds. But you can get an idea then of the strength of them. And let's take a look at this example. We're just going to look through these three compounds. We're going to decide what type of forces are present here. When you're looking at questions like this, you have to look through each, decide if the overall molecule is polar or nonpolar, or if it's an ionic compound. And then once you know whether it's polar or nonpolar, then you can really distinguish the types of intermolecular forces that will be present. Okay. So we have NCl3. We have H2O. We have Br2, which they've written out for us as BrBr, but we should be able to see those things as the same thing. KCl, and then NH3. So again, pause for a second and try this on your own. Okay. For our NCl, we'll come up with a structure that looks like this. And we're going to see that we have that lone pair up here. We're going to have 4 electron groups with 1 lone pair. So this is going to be a trigonal pyramidal shape. With a lone pair. So it's going to be polar. There's no hydrogen bonded to the nitrogen. So we know that the molecule is going to have dipole-dipole forces and dispersion forces. because everything has dispersion forces. Okay. Let's sketch out our H2O over here. We've sketched out H2O a bunch of times, so I don't have to really talk through how we're getting there. We know that the H2O molecule is a bent molecule. We see that there are the two lone pairs here, so we know that this is going to be polar. And we see that the hydrogen is bonded to the oxygen, so that means that we're going to have, I'm going to abbreviate it as H bonding for hydrogen bonding. It's also going to have dipole-dipole forces, and it's going to have dispersion forces. Okay. Just because it has the strong one, that doesn't mean it doesn't also have the weaker ones. It's just that the strongest one is going to dominate the other two. Okay. That's for our H2O. For our Br2, it's two atoms that are the same that are bonded together. This is going to be nonpolar. And if it's nonpolar, the only type of force it can have is dispersion forces. For our KCl, we have a metal and we have a nonmetal. This is an ionic compound. Ionic compounds have ionic bonding, and that's it. And for our last example, we have our NH3. We have our shape here is going to be trigonal pyramidal. We see that lone pair right there, so we already know that it's going to be polar. And it also has hydrogen bonded to the nitrogen. So here we're going to have hydrogen bonding, dipole-dipole forces, as well as dispersion forces. Okay. And that is what we're going to need to know for our intermolecular forces. And that is the end of chapter 6.